Okay, let's unpack this. We've got a really weird paradox about electric vehicles today. You buy this incredible futuristic machine, right? It's heavy, it's insanely fast, perfectly silent.
Yeah, exactly.
But if you just throw a standard set of tires on it, your battery range suddenly tanks, the tires go bald in a year, and the cabin sounds like a wind tunnel.
Right. It's like this hidden tax of early EV adoption.
Yeah.
And for this deep dive, we're pulling from Continental's technology specs, a stack of tire industry data, and this really fascinating physics thesis out of Chalmers University.
Yeah, we really want to figure out what happens when all that next-gen tech actually hits the pavement. So let's start with why standard tires fail so quickly. I mean, EVs are heavy.
Extremely heavy, yeah.
They're usually carrying an extra, I think, 400 to 600 kilograms just in battery weight, which is literally the weight of 2 grand pianos.
Right.
Plus, you have something like a Tesla Plaid dumping over 1,000 Newton meters of torque, just instantly. It's like a massive bodybuilder trying to run sprints in cheap flip-flops. The footwear just gets obliterated.
I love that analogy. And what's fascinating here is the underlying physics. A standard tire on an EV might only last, say, 28,000 kilometers, compared to 40,000 or more on a gas car.
Wow, that is a huge drop.
It is. And the Chalmers thesis zeroes in on a specific physical phenomenon here called hysteresis.
Hysteresis. I've heard the term, but how does that actually destroy a tire?
Well, think about bending a thick metal paperclip back and forth repeatedly.
Oh, right. The metal deforms and gets super hot.
Exactly. Rubber does the exact same thing. Under the massive weight of an EV, standard rubber drastically deforms right where it meets the road.
Okay, so it sort of squishes down.
Yes, and that continuous flexing absorbs energy and generates an enormous amount of heat, which literally breaks down the tire from the inside out.
Oh, wow. So it's not just the friction of the tire scrubbing against the asphalt from all that instant torque. It's the internal structural flexing that's cooking the rubber.
You nailed it.
So how do you stop that flex without just, making the tire out of solid steel?
You engineer an internal skeleton. Modern EV tires use highly tensioned nylon reinforcement layers. It acts like a rigid structural corset inside the rubber.
Wait, a nylon corset, built inside the tire?
Yeah, exactly. Combined with much higher air pressures, around 3.2 bar, this corset physically prevents the tire from bowing and flexing under the EV's weight.
Okay, so no flex means no hysteresis, which means drastically less heat.
Right.
But wait, if you pump a tire up to 3.2 bar and wrap it in a rigid nylon corset, doesn't that make the tire incredibly hard?
It does, yeah.
I'd imagine a rock-hard tire is terrible for actually gripping the road, especially in the rain.
That is exactly the engineering puzzle. If the tire is too stiff, you slide right off a wet road. But if it's too soft, the rolling resistance from that hysteresis drains up to 15% of your battery range.
Wait, 15%? Just from the tires?
Just from the tires. So to fix this, chemists radically alter the rubber compound itself, adding up to 35% silica.
And what exactly is the silica doing at a chemical level to solve that?
It works almost like a microscopic shock absorber. Silica bonds with the rubber polymers in a way that makes the tread block incredibly stiff against macro forces.
Like the overall rolling of the heavy car.
Right, exactly. So you don't lose forward momentum and battery energy. But at the micro level, the rubber remains highly elastic.
Oh, I see. So it can still conform to the tiny, rough textures of the asphalt to maintain grip.
You got it.
Okay, so you've got this highly inflated, incredibly stiff, silicon-infused drum wrapped around the wheel to handle the weight and save the battery.
Yes.
But a tight drum rolling over rough asphalt has to be incredibly loud, right?
Oh, very loud.
Yeah.
By solving the weight and range problems, engineers essentially built a perfect acoustic resonator.
And since an EV doesn't have a roaring combustion engine to mask the sound, that road hum has to be deafening.
It becomes the dominant noise in the cabin. It travels right up through that stiff tire.
So how do you deaden a rolling drum?
Well, companies developed acoustic dampening solutions, like Contessa Island. They literally glue a continuous strip of specialized polyurethane foam directly to the inner surface of the tire tread.
Hey, they just glue foam inside the tire. I would think gluing a chunk of foam inside a tire spinning at highway speeds would completely throw off the wheel balance.
You would think so, but this specific foam is incredibly lightweight and porous. It doesn't interfere with the tire's rotation at all.
Oh, fascinating. So what does the foam actually do?
Its porous structure traps the sound waves that are bouncing around inside the air cavity of the tire. It absorbs the vibrations before they can travel up the axle.
Wow. Does it make a big difference?
It cuts perceived cabin noise by up to 9 decibels.
9 decibels is huge. That's like the difference between standing next to a busy street and stepping into a quiet room.
It fundamentally changes the driving experience.
Yeah.
And, it really highlights how, for these vehicles, rubber just isn't rubber anymore.
No, clearly not. It's a highly engineered piece of technology.
Exactly.
So the next time you're shopping for EV tires, you'll know exactly why you can't just grab whatever is cheapest on the rack. But I do want to leave you with a fascinating paradox from the research to ponder.
Oh, right, the environmental aspect.
Yeah. Even with the nylon corsets and silica compounds, these heavy EV tires still wear out faster because of that massive instant torque, meaning they are shedding fine particulate matter onto our roads at a much higher rate.
Yeah, it's a huge issue.
It makes you wonder, as we transition to electric, are we simply trading tailpipe emissions for tire pollution?
It's a really complex physical trade-off and definitely a vital question for the next generation of automotive engineering.
Something to chew on during your next perfectly silent commute? Thank you so much for joining us on this deep dive.